Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. In this episode, we're joined by Garrett Hoffman, Director of Data Science at StockTwits. Garrett and I caught up at last month's Strata Data Conference where he presented a tutorial on deep learning methods for NLP with emphasis on financial services. StockTwits is a social network for the investing community, which has its root in the use of the cash tag on Twitter. In our conversation, we discuss applications such as StockTwits' own use of social sentiment graphs built on multilayer LSDM networks to gauge community sentiment about certain stocks in real time, as well as the more general use of natural language processing for generating trading ideas. Before we dive into the conversation, I'd like to send a huge thanks to our friends at IBM for their sponsorship of this episode. Interested in exploring code patterns leveraging multiple technologies, including ML and AI? Then check out IBM Developer. With more than 100 open source programs, a library of knowledge resources, developer advocates ready to help, and a global community of developers, what in the world will you create? Dive in at ibm.biz/MLAI podcast and be sure to let them know that TWiML sent you. And now, on to the show. All right, everyone. I am here in New York City at the Strata Conference, and I am with Garrett Hoffman. Garrett is the Director of Data Science at StockTwits. Garrett, welcome to This Week in Machine Learning and AI.
Thanks for having me, Sam. It's fantastic to be here.
Awesome. I am always super excited when I'm interviewing someone and they say they listen to the show and enjoy the show. So thanks for offering that. Why don't we get started by having you tell us, for those who aren't familiar with StockTwits, what's StockTwits all about?
Yeah, I'd love to. So StockTwits is a fintech financial technology company. We're based here in New York City. And our core product is the StockTwits.com or the StockTwits mobile app, which is a social network for the finance community. So kind of like a LinkedIn meets Twitter specifically for traders and investors. So people who are interested in the market can come on, connect with each other, share ideas, learn from each other, and most importantly, they can enjoy participating in the markets and investing even more by sharing in that experience together. Our core user is the millennial investor who we know is digitally native, increasingly social. This is a group that really loves social engagement around the decisions that they're making. And we've seen companies like Amazon facilitate this in e-commerce when someone's looking to buy something through going through reviews, talking with their friends about kind of the stuff that they're purchasing. And as a company, we really see ourselves as a platform where people can come to engage in this type of social interaction around the decisions that they're making in investing and financial services. So right now, conversation centers mostly around individual stocks, but our new product that we actually just launched called Rooms allows the community to start to self-organize around specific topics that they're interested in. And that's really exciting for us because it allows people to dive deeper in detail. So maybe like they want a room just to talk about Apple products and what that might mean for the stock. But it actually also helps conversation grow bigger and more general. Maybe people want to talk about other financial services like robo-advisors, like general like insurance, stuff like that. So it's really giving the community a platform to talk more about financial services in general or specific topics that they're interested in.
And I've got this impression that StockTwits grew out of the stock tag on Twitter. Is that the case or?
Yeah, so our founder, Howard Lidzin, back, I think it was 2009, invented the cash tag. And so this was a $sign in front of a ticker symbol on Twitter. And we were actually partnered with Twitter using the Twitter API to kind of search and filter Twitter for tweets specifically that had a cash tag. So it was kind of a filter on the Twitter API A few years later, we actually left the Twitter API and became a standalone platform. So it was born through the cache tag. The cache tag is our main mechanism for indexing conversations to specific stocks. But StockTwits today, it's its own standalone platform, but it is that microblogging, real-time Twitter-like format of discussion.
And what's your background?
Yeah, so in undergrad, I studied mathematics and finance. I got exposed to a lot of like the core ML mathy concepts, matrix factorization, eigenvectors, optimization, statistical learning. But I'd say my first introduction to kind of machine learning as like a field that was more than just like the sum of these individual parts that I was learning was when I started researching topics for my undergraduate thesis and came across neural networks. I really wanted to study something that was math as used in the finance industry to kind of tie both my fields of study together. And I saw that people were starting to like resurface neural networks to do forecasting on stock prices. And I actually decided to pass on that topic. I was like, oh, this was done in the 80s. It's kind of been explored already. I couldn't have been more wrong about how prevalent it would be a few years later. In fact, I was more interested at the time in kind of probability theory, stochastic calculus, random processes. So this was 2011 when I finished undergrad. And at the time, the default job for people who studied math and didn't really want to teach was an actuary. So I got a job as an actuary at Xerox, part of a smaller business group called Buck Consultants that they owned. A lot of people don't know that Xerox played in kind of the consulting playground, but I did actuarial consulting around benefit plans. So valuing retirement plans, valuing health plans, executive stock option plans, kind of working on the investment strategy around the funds that pay those types of benefits. And being an actuary is a phenomenal profession, but after a year or so, I kind of realized it wasn't for me. I wanted to have more of a tangible impact and be able to kind of like see the impact of the models that I was creating and of the analysis that I was doing. So I really liked my company and I liked the space. I'm very passionate about financial wellness and financial literacy and helping people gain the knowledge and tools that they need to kind of be independent and wade through a very complex world on their own. So I really became interested in how can we help our clients help their employees make better decisions around their benefits. So this was more of like a behavioral psychology, behavioral economics problem, and I think was my first cross in my professional life of kind of leaving the world of actuarial problems and the types of stuff that actuaries normally think about to entering kind of a data science problem, a problem that could be solved using machine learning and data science. So I actually spent the next few years still at that company doing kind of like half actuarial stuff, half product development for these new solutions. They actually started to take off. We got a few client projects. Xerox actually let me take a sabbatical. They sent me to Metis Data Science Bootcamp in New York City to kind of true up my knowledge, fill in the gaps more on the product and delivery side, like how are solutions in data science and machine learning scaled and delivered, just because as an org, we were kind of wading through new territory. No one really had that knowledge of, okay, once we've done the modeling and done the technical stuff, like what are clients who are looking for these solutions actually looking for when they ask someone to help them with it. So stuff like productizing data through APIs, building applications with data science, stuff like that. I ended up going back to Xerox for about 6 more months and realized that I really wanted to go somewhere where I could really shape like a consumer-facing product. I wanted to be somewhere a little more closer to the technology industry. The actuarial industry is great, lagging maybe a little bit behind in terms of like using cutting-edge technology. So at that time, I started looking for new opportunities. I ended up at StockTwits. It was kind of a great marriage for us where I'd have a treasure trove of data being close to like being centered around a social network, and still kind of at an org where their goal was to help people understand this really complex world of finance.
And so you did a tutorial actually here at Strata on the use of deep learning methods for natural language processing, with a particular emphasis on financial services and some of the things you're doing at StockTwits. What are some of the ways that you use NLP at StockTwits?
Yeah, so our core data that we have available to us at StockTwits is, of course, raw messages that people are writing, ideas that they're generating. So we're working a lot with just raw text data. And as a data scientist at StockTwits, I see the core mission of our team is to really improve the user experience and improve the product through data. And so for us, and a lot of how I see machine learning, like what machine learning aims to do is to actually kind of like shrink the world. And so StockTwits, there's real-time information flowing by really, really quickly. Things change super quickly. It's a real-time stream. So to the extent that we can use data to build data products to kind of help people discover like snapshots of what's going on right now, help them really find stocks that they're interested, help them find people that they're interested in. That's really how we're using data. So one of our biggest uses for NLP is actually our social sentiment model. So we like to summarize the stream of what's going on with sentiment graphs. So we try to keep real-time updates of how our community feels about a certain stock, and we're doing NLP modeling to extract financial sentiment from all the text data that's coming in, and then aggregating that at an individual stock level to kind of see how that's moving and see how that's changing over time. So that lets people come in and see maybe they've done some research off platform. They want to just check out what people are saying on StockTwits, even before wading through, thousands of messages in a real-time stream. They can have this nice little snapshot of, how does the StockTwits community feel? Are they overly bullish? Are they more bullish than they typically are? Has there been a drastic rise or fall in sentiment in the last few days? Stuff like that.
So your talk was on deep learning methods. What are some of the methods that you apply to solving those kinds of problems?
So when we think about sentiment, we're typically in the realm of RNN. So we're using multi-layered LSTM networks to just extract a sentiment, a bullish, neutral, and bearish signal. And we're fortunate enough that we have users have the ability to tag their messages with sentiment when they post it. So we've been able to inherently gather labeled training data through general usage of the app and through people tagging their messages. One of the reasons we go on to model sentiment further is only about 20 to 25% of messages are tagged. So by building a model around sentiment, we can expand that coverage to 100% of the volume instead of just this very small subset of tagged messages. We typically have to supplement our tag data through manual curation, just kind of validating that those tags exist. So we use LSTM networks. It's really a great method for capturing those dependencies across as it changes, capturing dependencies of the language and the relationship through text through a nice sequential model like RNNs. And LSTMs help us capture more nuance in the language. So sometimes you get a really straightforward message like "I am bullish." Maybe you get, and so that's really obvious. And then sometimes it might not be so straightforward. So an example of that might be someone saying "Oh, Tesla here looks really, really high right now. I don't think I'm a buyer. If it dropped maybe down to the 200 range, then I would definitely get in." So if I'm using a method or a model to classify that statement, Typically, you're making classifications at the end of your sequence. The end of that sentence makes it seem like that person might not, that they are bullish, that they're going to be a buyer. But LSTMs allow us to capture kind of the state of that sentence to know, at the start of this sentence, this person was pretty bearish. And so LSTMs allow us to retain that information throughout the entire sequence that we're trying to classify.
What challenges do you run into when you're trying to develop these models based on LSTMs?
Yeah, so I'd say our biggest challenge is probably the domain-specific nature of the language. So like bear and bull in a generic setting of language processing are just animals. Like cup and handle is like a stock pattern. So the world of finance has a ton of vocabulary that is very niche to talking about finance itself. So this is something we actually talk about at the talk in the training, is this dealing with this domain-specific language and tackling it through leveraging what we can from the open source community. So there's a ton of pre-trained word vectors that exist out there, but those might not get the job done when you have a domain-specific language. So we actually talked about the idea of starting with pre-trained word vectors, but building on those through training additional word2vecs on your corpus that's specific to your domain. So maybe instead of seeding, like if you're going to train a word2vec model to get, efficient representations of your language and your vocabulary, instead of seeding randomly, you can seed with a pre-trained word vector, maybe out of Google News, and then train over your corpus so that it can kind of start to learn language that may exist in a pre-trained vector, but can adjust that to specifically model your language inherently. And you get a nice platform to jump off of because Google's done a lot of legwork to train vectors on billions and billions of news articles.
Of the various pre-trained word vectors out there, Glove and Google News and others, is Google News the one that most closely matched to your use case?
So we actually like starting with the Twitter Glove vectors, mostly because to capture like the syntactical nuances of how people talk in short form text over social media. So we found that the Twitter data glove was a good launching point, and it's actually we saw pretty decent results just using those vectors alone. So one of the takeaways and something that I'd push to anyone who I'm talking to this stuff about it is there are people who are a lot smarter than me who have done a lot of legwork, and like us as practitioners are fortunate enough that they open that work for everyone else to use. So even though stuff may not seem like it's applicable, don't let that stand in your way to just get out there and getting started. Training custom word vectors is no small task. It requires a ton of data. It requires potentially days or weeks of training. And that's the result of that. You're not even positive if it's going to make that big of a difference in your downstream modeling task. So something I like to stress is wherever you can, start with like stand on the shoulders of these giants who did this work before us, and try to kind of start with that, see where it gets you, assess the situation, and go on from there.
Is there a method to do like composite training with multiple pre-trained word vectors? Like, is there a way to combine Glove and Google News?
I haven't done anything like that. I would imagine there could be some like meta modeling or ensembling on top of it, where this may or may not exist. There might be some research on top of this, but I couldn't see why you couldn't maybe, instead of, in a traditional word2vec model that you're starting from scratch, your input is a one hot encoded vector of a word. Your output is one hot encoded vectors of the context of that word. I could see maybe some method where the input is some like concatenation of existing word vectors, and your kind of hidden layer is still learning like how to combine the best things from those existing word vectors to learn the context. Because at the end of the day, what Word2Vec boils down to is we want to learn some efficient representation of words such that our representation reflects semantic and syntactic and contextual meaning across multiple words. So I always like to say that the philosophy of Word2Vec is a quote from J.R. Firth, who's a famous English linguist, who said, "You shall judge a word by the company it keeps." So that's basically the philosophy of Word2Vec, is we just want to ultimately end up with representations that kind of can be shared across syntactical meaning. So if I have the word good and I have the word great, I should have a representation of that word such that my LSTM model can leverage the fact that those words are similar to make the predictions that it needs to make. So no matter what your input is, that hidden layer, by nature of the way you construct that prediction task of predicting context, it's going to force words that show up in similar contexts to have similar representations. So I'd imagine if you start with pre-trained word vectors instead of one hot encoded, it might be able to kind of pick out the best stuff, even for your specific use case. So that could be a good approach. Maybe we'll go back and I'll put that on our backlog to experiment with.
You mentioned that you use specifically multi-layer LSDMs. What does the multi-layer refer to there?
So the multi-layer just stacks multiple LSTM layers on top of each other. So something I stress in this training, and I think anyone who's kind of learning about LSTMs, is there's a lot of things called like layers and like a lot of dimensions. So like you have an LSTM cell with a hidden layer, and then you might have multiple LSTM layers. And then within each cell of an LSTM, there's kind of like 4 layers that are doing their things to maintain the state and retain information from the past sequence. So I try to, when I'm doing this training, make it super approachable, like kind of make sure that people are understanding what that distinction is. And so a hidden layer is just like some vector that lives inside the LSTM cell. The 4 like feed forward layers in an LSTM cell are just kind of moving that state through different gates and through activation functions. And when I say multi-layered network, so now we're at a network level, we're outside just a cell of an LSTM, we're really talking about stacking 2 whole LSTM layers on top of each other. So if you think of like a graph pointing upwards, like you'd start with your embedding lookup. So you'd input your word at any time. The first layer would be your embedding lookup. That embedding would get passed up to the first LSTM layer. It would do its thing. Part of that is it would output. The output from that LSTM layer then goes as the input of a second LSTM layer. And then that LSTM layer does its thing. Then you take that last final state at the end of the sequence, pass that up to your fully connected layer, and do kind of your softmax prediction or your sigmoid prediction, depending on how many levels you have. So when someone's referring to multi-layered LSTM network, they're really referring to 2 steps of LSTM. The first step, where your input is actually the word vector associated with each word, and the second layer is actually the LSTM output at that time being passed as the input to the next LSTM layer.
And how do you know when you need to do that? What's the intuition for what these different layers are doing?
Yeah, so I'd say a lot of this is learned through observing what's happening, cross-validation, performance on a validation set. I do think there is this understanding of like the complexity and the nuance of the text that you're working with. Basically, all an LSTM is doing is it's trying to trying to learn a state of your sentence that kind of summarizes all of this information. And I know the word state can be so abstract, so that I try to also stress like what that means. When we say state, basically we're trying to capture all of the semantic and contextual nuance of a sentence in like a 128 dimensional or 256 dimensional vector. So your first LSTM network is going to learn a state such that, maybe one dimension of that state refers to it was this sentence negated at any time. Another dimension or a linear combination of dimensions might say, is the last sentiment I saw bullish or bearish? And then that state can kind of be combined and it'd say, okay, like I saw bearish sentiment, but I saw negation. So now I actually know to predict that this is something bullish. And so stacking layers on top, just continual, like they allow you to do more linear transformations on that state to try to learn a richer representation. At the end of the day, what matters is that your prediction task is as accurate as you need it to be. So we're not gonna, pull out our LSTM states and examine them and be like, okay, like I can see everything I want to be represented. So as a lot of this comes down to just like validation accuracy, observing these things through training. Deep learning can be really tough to do this parameter tuning. If you're a small company and you don't have a ton of GPU resources available to you, these things can take a long time to train to be effective. And some people can't just spin up like 10 concurrent GPUs and monitor all this stuff as it's running. So TensorBoard is a great tool that we try to leverage, where you can monitor something as it's training. And if you can see like, oh, our loss stopped going down, let's cancel this and try something else. So you can kind of see the model learning in real time. You can benchmark it against like your current best model. And if it's not on track to beat that, you're saying, okay, like let's cut this training short, try something new. Again, I'd always recommend to start simpler. Maybe start with one layer, get a baseline model. If you need to tune that better, start adding in more and more layers. I would treat that architecture like you would treat any other hyperparameter that you're trying to tune.
Okay. And so the layers aren't differentiated in any way. Of course, they're hyperparameters, but other than that, they're not fundamentally different. They're just, multiple LSTM layers stacked on one another or feeding into one another. And like you said, you treat it as a hyperparameter, try adding another one. What's the most number of stacked LSTM layers you've seen?
For what we do, we've probably never explored anything more than 3. I'm not sure if other existing research out there, like people using LSTMs for more complicated learning tests, might be stacking on top of each other. Bidirectional LSTMs is something else that we've explored. And what we've found is actually, if you choose to go with a bidirectional LSTM, for those not familiar, it's kind of a bidirectional LSTM is 2 LSTMs. Just one reads your input text forward to backwards. The second reads your input text backwards to forwards. So it would start with your last token in your sequence and read it backwards. And then you'd kind of concatenate those into your output to pass up. So we've found that bidirectional with fewer actual layers stacked on top of each other can perform as good as a regular LSTM with layers stacked on top. And it kind of makes sense, because the goal, what these LSTMs are trying to do, is just learn this representation and learn this state. And passing in multiple layers, you're kind of maybe each network, while they look the same, they're learning different things. So maybe, the first LSTMs are like learning baseline state stuff. The second LSTM is really taking that state and finding the interactions with each other and how things in that state are working together to help in your prediction task. A bidirectional LSTM can do that in fewer layers because it's kind of seeing the text twice. So it's learning a state going forward. It might be picking up on other nuances going backwards and then tying those things together, where you can get away with a smaller architecture.
So LSTMs figure very prominently in the sentiment analysis that you're doing. Are there other techniques that you bring to bear?
Yeah, so something I get really excited about, and we're kind of just starting research on this. It's kind of a future frontier where we're hoping to get to. One of the main goals, like I said before, is we want to help people find what is relevant to them and wade through what seems like a suffocating amount of information to find what they need. This actually aligns really well with a common problem in active investing, where idea generation is almost parallelizing. Like, it's really hard to get into investing because you need to kind of do the research, come up with the ideas. What do I want to invest in? So, to the extent that we can help people find individual stocks, help people find individual content, or help people connect with other people that will help them generate those ideas, it's things that we're interested in. So, besides just sentiment, we are looking at this is actually still related to, we're exploring LSTMs, we're exploring convolutional neural networks for this, but doing more representation learning for the conversation going on, or like between users on certain stock streams. And we want to basically do this for recommendation purposes. So this, I think, is this newer trend with neural networks and deep learning that we're seeing more recently, where we have some prediction task. We're learning a state. So this state might be like the final hidden state in an LSTM. It might be like the final fully connected layer in a convolutional neural network. And you might be predicting something. That thing could be arbitrary. And at the end, you're kind of like throwing that task away, and you're left with this representation that you can put in an embedding space to kind of then do something like k-nearest neighbors to find similar things. So through conversation, we're exploring, can we like embed like StockTwits messages in a message space where we can see like the types of messages that a user typically likes to engage in, maybe the types of stocks that they're engaging in. Maybe we have another embedding space around stocks that kind of can say, okay, like, you're interested in these stocks. Here are stocks that are similar based on this embedding, and then find, the best messages about that stock from this message embedding space. So we're exploring convolutional neural networks to basically, not for a prediction task itself, but to kind of create this this like embedded space of users, of messages, and of stocks themselves to kind of to make recommendations.
And so in this case, what's your input?
So the input would still be the text data itself. And
your convolutions are across the vectorized representation of the text input?
Yeah, so this is a technique. There's a canonical paper that's convolutional neural networks for text. It was kind of the first paper that explored this. And basically, we have a one-dimensional convolution. So your input is exactly like you said. It's a matrix, 2 dimensions. Down the rows would be the words in your sequence. Across the columns is your each dimension of your word vector for that for each word. And we do a one-dimensional convolution because we're just taking windows and sliding them down across the entire word embedding. So you're kind of capturing features generated through words that appear next to each other, and you would kind of have parallelized windows of different lengths, just like you'd have filters of different sizes for a 2-dimensional convolution. And this intuitively, this should make sense, because when you're dealing with images in a convolutional neural network, information is local to an individual pixel. So an individual pixel is just one entry in your input matrix. So when you have this 2-dimensional window that you're sliding over it, pixels go in both dimensions. When you're dealing with text, information isn't local to just like one dimension of your word embedding. Information about that word encompasses maybe like all 50 or 250 dimensions of your word embedding. So the one-dimensional convolution makes sense because you want to make sure when you're representing a word, you're not excluding certain dimensions of your word embedding. Yeah.
Interesting. So are the network architectures here, are these kind of simple CNNs, or have complex network architectures like Inception and all that kind of stuff evolve for textual data?
In my experience, I've seen fairly simple CNNs. We would probably do maybe have 4 or 5 window lengths. So like taking 3-word, 4-word, 5-word, 6-word windows, maybe have 100 to 150 filters of each size, and then kind of branching off into like maybe those 4 or 5 parallel neural net, like convolutional neural networks that then end up at some point like concatenating back together for like that last fully connected layer. So I'd say it's a fairly simple architecture, but you get a little bit additional complexity if you kind of are doing a couple different size filters in parallel and then kind of bringing them back together. So I'd think of it like 4 different CNNs, each branching out in their own direction and then ultimately coming together at some point to have a final prediction made.
I'm wondering if there are other tricks that you're kind of layering onto the CNNs to help here.
No, I mean, we're still pretty early in our research at StockTwits on this, so we're trying to start simple. We drew a lot of inspiration actually from companies like Spotify who are using these types of methods to kind of do music recommendation. And for us, stocks are very similar to music. So like you kind of have these like genres and like playlists where you can kind of tie stocks together through conceptual themes. So like stocks related to self-driving cars, stocks related to AI, tech stocks. You kind of have this engagement. So like people are listening to different music, people are like engaging in different stocks. And then you actually have kind of a similarity for price movement of a stock. Like if you're analyzing music and you're actually looking like at the notes, like the structure of a note or the structure of music at that level isn't that dissimilar to just like looking at a stock price change over time, where like the chart is your the chart is kind of your bars, and like each time frame is kind of notes. So we try to draw inspiration from other leaders who are doing this type of work. So they're probably quite a bit ahead of us. They might be doing a little bit more complex things. But as far as CNNs, we try to keep it fairly simple.
Okay, so we've got LSTMs, we've got CNNs. Are there other techniques that you tend to use to solve some of these problems?
Yeah, so another area that we're starting to research is text summarization. So like I said, the streams, the velocity is very, very high. Information is coming through. If something is trending, like if something crazy happened, for example, like if Elon Musk is going off the deep end and Tesla is tanking, we may be seeing like upwards of like 500 messages come in like a minute. So it's kind of really hard for like maybe someone who hasn't developed a really refined process for how they like to use StockTwits to come on to StockTwits and not be overwhelmed by the sheer amount of information that they're seeing. So text summarization is something that is super interesting to us. We curate news as well, so news summarization is like a more well understood problem. We're really curious, can we apply those techniques to a stream where we can maybe extract the most important things that are going on in the last hour from what people are saying about the stock, and maybe have those as bullet points when you're going to the Tesla page to kind of ease in and still get, okay, so what are people saying about this stock without, being like, oh man, like there's just stuff coming in so fast I can't really deal with it. So for our text summarization, we've been still focused in the RNN domain, but more focused on kind of these sequence to sequence models. So encoder decoder networks with attention.
And so how do those work?
Yeah, so I believe
or even better, how do you explain them? How did you explain them in your tutorial?
So RNNs are very robust. There's a lot of different flavors of LSTM. So when we're dealing with the sentiment classification problem, we're dealing with kind of a many-to-one RNN, where our input is many, the different words in our sentence one at a time. And then after we've seen all those words, we want to make a single prediction. Is this bullish? Is this neutral? Is this bearish? When we're dealing with problems like text classification, our input is a sequence and our output is a sequence. So we're inputting the words of our original text. Let's just say we're dealing with a news article, and then we want to output another sentence that is just a summary of that text. So our output is multiple tokens of our summary. And so the way we can handle that is kind of stacking two RNNs on top of each other, not like we did it before, but kind of letting, it's referred to as an encoder decoder. So we have a first RNN that's taking in our inputs, our input sequence, and it's kind of learning a state of that input sequence. And then we have a decoder RNN who is taking in that state from our encoder and kind of decoding that and picking what, kind of generating what the best summary would be. And in the past, the original models of this had the encoder and the decoder talk directly to each other. So the encoder would come up with a final state. It would pass that final state to the decoder network. That final state would be the initial input to the decoder network, which would then kind of learn, like it would maintain its own internal state to try to say what word from my vocabulary has the best probability of being the next word. So the decoder RNN is really trying to predict, given the state that I have and what I just said the first word of this summary is, what's going to be the next word in our summary. So this is truly like language generative modeling, where we have some vocabulary and we're trying to generate language that makes sense. And this original model kind of had its drawbacks, where we were asking a lot of the encoder RNN, where we're saying encode everything that you have to say in this one final state that's going to be passed to the decoder network. Okay. And it was actually, I think, neural machine translation that introduced this idea of attention. And so now attention is this layer that lives between the encoder network and the decoder network that basically says, at any point when we are decoding, let me look back at the entire input sequence and let me focus on where in the input it is important for me to make my prediction on what the next word is going to be.
And how have you found this this model to perform for summarization? Are you getting good summarization of?
You can get pretty decent summarizations on news. News is like a very well-structured input. A just random sequence of tweets is not very well-structured. So we still have quite a way to go before I think we get anything that we would put into production for tweet summarization.
And it's also you're not necessarily trying to summarize an individual tweet. It's more like corpus summarization, right? You're trying to pick the main elements across multiple tweets. And so do you like just concatenate them all together, or is there some that seems like you're losing something if you do that?
Yeah. So I think how we've approached it is we've tried to kind of explore with this idea of a three-dimensional input to your RNN. So like traditionally inputs to RNNs are two-dimensional in respect that you have a sequence of words. So your sequence of words is the first dimension. Your sentence could be 10 words. And then each individual word that you're inputting has like a one row with 300 columns of your word embedding. So we were playing with kind of a three-dimensional input where your first sequence is a stream. Your second sequence is a tweet in the stream, and like your third dimension is like the words in that tweet. And I think you kind of hit the nail on the head, where we are probably not being fair to our LSTM network. We're probably asking it to do too much by trying to treat a stream like it is one cohesive document, when in reality, I think our next direction of research is going to be more, okay, maybe don't summarize a whole stream, but can we pick out an individual tweet that we think is really good and that encompasses like a broader trend that we're seeing across multiple tweets? So maybe it's not necessarily framing it directly like you would frame a news article summarization, more framing it like we're not generating new language, but we're finding a tweet that is representative over like a broader concept that we can identify in a stream.
Does transfer learning apply in this space at all? Like, we've got the pre-trained glove vectors, and is there anything that can be used to accelerate a summarization task so that you're not pre-training everything from scratch or training everything from scratch?
Yeah, definitely. So the NLP community is starting to make a lot bigger strides in getting to effective transfer learning for language tests. I still don't think it's close to where the computer vision community is, but progress is definitely being made for kind of generic things. There are pre-trained models out there from... They're not kind of like the computer vision where there's like these go-to trained models, but you can find decent research out of there. There's a paper I really like that I've drawn a lot of inspiration from Abigail C. on pointer networks. And so pointer networks are this extension of just base like vanilla attention models, where you're also kind of training this parameter called a pointer that's saying anywhere in... When I'm predicting the next word in my summary, do I want to just kind of generate a new word from my generic vocabulary, or do I want to pick a specific word from the input text to use here? So I think one of the biggest problems that people were seeing in summarization was that it was getting baseline facts wrong from the input text. So like if I was summarizing a news article that Tesla dropped 10% pre-market, the traditional techniques for having a tough time extracting that 10% figure. So this pointer can basically say, okay, like I know that I'm about to pull a figure out. I'm gonna grab vocab from my source text and not try to like pick a needle out of a haystack of what this metric might be from like all the metrics I've ever seen that live in my vocabulary.
And is this all deep learning based, or is there like some tokenization, entity resolution, that kind of thing happening up front?
I believe it's end-to-end deep learning based. Yeah, so I think there's I'm not sure what they used for the word vectors, or if the word vectors are just learned in an end-to-end fashion, but there is a pre-trained model out there. Like they open sourced all the code from this model. It was trained on CNN and daily news data. And so there is a pre-trained model out there that exists that was kind of our first step of saying, okay, like if we just took this model and ran financial news through it, would we get anything? Like, would it be able to be applied? I also think you could kind of use that model as a baseline and then retrain on your specific data. I do think in our case of like trying to summarize tweets, we're kind of starting from scratch. I don't know how much transfer learning is there. I think where transfer learning comes into play for NLP is really, can we learn, like, do we have greater representations for more generic text at like a high level language modeling text? So I think when you're getting to like generative language, I see the future of transfer learning and NLP being like, okay, here are these good models that kind of like help us generate text. So like they learn kind of just like the state of a pre-trained model for computer vision is kind of learn these nice feature representations for different like parts of an image or different objects that appear in an image. Can we learn just like really good generic representations for how text interacts with each other, how words interact with each other to generate like sentences and language that makes sense? And then starting with those representations is kind of to be the first steps of your model, and build maybe mini models on top of that, if that makes sense.
No, it does. Well, Garrett, this has been great. Are there any kind of words of inspiration or wisdom that you would leave with folks who want to start exploring some of these techniques more?
My best advice would be dive in. I think you can spend months, probably even years at this point with all the information that's out there, trying to learn, trying to figure out exactly what's going on, trying to just become an expert. But really, no one's an expert. We're applying these methods to new problems that really don't necessarily have a solution. They have like the best solution that we have for them today. And you're really not going to be able to know everything before you dive in. You're going to learn a lot as you're going. So my advice would be, don't be afraid. The training I offer tries to kind of make deep learning methods accessible, because I think once you dive in, you'll realize that deep learning isn't that far of a jump from what you're doing today. So yeah, just don't be afraid. Just dive in head first.
Well said. And you mentioned that you've got code from your training in a repository and the slides and all that kind of stuff. And you'll get that link to me. We'll get that link on the show notes page. Anyone that wants to follow along with the material that you presented, they'll be able to do it there.
Yep, we'll do.
Awesome. Thanks so much, Garrett.
Great. Thanks for having me, Sam. It's been great.
All right, everyone, that's our show for today. For more information on Garrett or any of the topics covered in this episode, head over to TWiMLAI.com/talk/194. If you're a fan of the pod, we'd like to encourage you to visit your Apple or Google podcast app and leave us a 5-star rating and review. Your reviews help inspire us to create more and better content, and they help new listeners find the show. Thanks again to our friends at IBM for their sponsorship of this episode. Be sure to check out IBM Developer at ibm.biz/MLAI podcast. As always, thanks so much for listening, and catch you next time.